this thing set up, the angle was 0 degrees. In other words, the total magnetic field was parallel to the magnetic field of the Earth when there was no current. So now what we're adding is two magnetic fields that are at right angles to each other. Now the only reason they're at right angles is because we made for sure, as nearly as possible, that the compass needle was in the plane of that coil to begin with. So that's going to be an error right there, right? That's going to be off by a couple of degrees, right? Now where will a couple of degrees be most important? When we're at 10 degrees. So this is going to be our crappiest measurement, because being off by a couple of degrees at 10 degrees is much more important than being off by a couple of degrees at 60 degrees. So that's the kind of thing I need to hear in your conclusion, that you're being thoughtful about these things. Okay. So the angle now that we're measuring, the total magnetic field, this is the compass needle here. So B total is the compass needle, because the compass needle doesn't know anything other than the total magnetic field. So that's always pointing parallel to the total. So the angle theta then is which one? So this is perpendicular to the coil. This is parallel to the coil. So the little angle is going to be which one? I don't know. I'm asking you as a rhetorical question. I don't know. I have to go look at it again. You can figure it out. You can tell me, but in the meantime, I'm going to look at it here. So the angle 10 degrees is the angle between the total magnetic field and the field of the Earth. So theta is the angle, because originally the compass needle was pointing this way, now it points that way. So it's a little angle. So the angle is between B Earth and B total. So the reason I'm struggling is because this picture, although technically correct, does not really describe what we have going on right now. Let me redraw it so that it describes what we have right now. In other words, right now the total magnetic field is just a little bit bigger than B of the Earth, right? Because it just moved a little bit. So this is what we have right now. V caused by the coil is N mu sub 0 times the 0.14 amps over twice the radius of the coil. That's B of the Earth, and that's B total. Again, the magnetic field of the Earth at this moment is much bigger than B of the coil because it only moved it a little bit. So the angle theta is this one. So we can say then, we know that the tangent of theta in a right triangle, tangent is always opposite over adjacent. When I look at this triangle, opposite is B coil, and adjacent is B of the Earth. So that says that the tangent of theta is equal to N mu 0 I over 2R B of the Earth. Now you notice that I wrote some things in parentheses. Look at the things that are in the parentheses. You notice all of those are constants. And notice that your final exam will include a properly labeled graph. So here's the thing you're going to graph. You're going to graph the tangent of theta as a function of current, what graph would you expect?
Direct.
A straight line, a direct relationship, and the slope of that line should be n mu 0 I over 2r BE. So you're going to get three different graphs, and I want them on the same graph. And why did I draw it this way? Because everything in there is a constant. So what should the slope of this one be compared to that one? 3 times as much, right? Proportional, and 3 times as much. Because I'm going from 5 to 15. Everything else is a constant. So I get 3 different lines on the same single graph. And we would expect that the slopes should be integer multiples of the first one. Whatever that one's slope is, that one should be twice as much, that should be 3 times as much. Again, these things belong in your conclusion. Okay? So let me get rid of some more paper here.